Welcome to the last lesson. So here's our last prep assignment. In our last prep assignment, we are going to start off going over how to put logarithms into the calculator and to get approximate values that way. And then we'll get into solving some logarithmic equations that are a little more complicated than we've dealt with before, and then some exponential equations that are a little more complicated. And we'll wrap up with some word problems that lead us to either exponential or logarithmic equations. And that's our game plan. So for starters, what we want to talk about is the common logarithm. So if you look at your calculator most likely has two different buttons for logarithms. It has one that is log and one that is ln. Now the log allows you to type in a logarithm that doesn't have a base that's given. So it's sort of similar to when we're talking about, let's say, variables. When I just say x, I don't write a coefficient of 1. I just assume it's there. Similarly, I don't write an exponent of 1. I just assume it's there. And similarly, when I have a square root, I don't write an index of 2. I just assume it's there. So when it comes to the common logarithm, so the log of x, there is a base that's there that's assumed that's not written. That base is a base of 10. Now it's called the common logarithm because it is the most common logarithm we would expect to see. Because when it comes to things raised to powers, 10 to a power is so common, we live in a base 10 world. Our whole number system is built on base 10, where each of the digits that we talk about are a power of 10. There's the ones place digit, there's the tens place digit, there's the hundreds place digit, there's the thousands place digit, and these are 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. So a base 10 is a very common base. So that's why we call this the common logarithm. The logarithm of base 10 is a common logarithm. And we just don't write the base. We just call it log and then the argument x. So with that said, it's important to realize, we've talked about this before as far as the level, that log and the argument are on the same level. We're not going to write this as log of x. That would be log base x, and then we would still need an argument. So they're on the same level when talking about common log, but that's what a common log is, and you should have a button in your calculator for this common log. This example that we're going to do is hopefully a very, very easy one. This one tells us use a calculator to approximate common log of 7 to 4 decimal places. And so literally all you're going to do is go to your calculator and type log 7 and hit enter. And then to round to 4 decimal places, it looks like it's 8451. Once we round that 4th decimal place up, again, I'll bring the full version up so that we can see it together. So the 5th decimal place was 5 or larger, therefore we round the 4th one up 1. And that's it. That's the start to figuring out how this whole common log thing works, is the fact that we can put a common log into the calculator. Now the other button on your calculator that is a logarithm is the ln button. Now notice this is ln. A lot of people misread this as in. That's not the case. It is a lowercase l and a lowercase n, and it is the natural log. Now natural log of x means the same thing as log base e of x. Well, what is e? So e is an irrational number, kind of like pi is an irrational number. So, you know, pi is 3.1415, blah, blah, blah. It goes on forever with no pattern. So that's kind of how we think about an irrational number. Square root of 2 is an irrational number as well. It's a number that can't be written as a fraction, and it's a decimal that goes on and on forever with no repeats, no pattern. That's an irrational number. So we give names to very common irrational numbers that we see a lot, like pi. Pi comes up a lot because it has to do with these circles. It has to do with the ratio of the circumference to the diameter. And so it comes up so frequently that we gave it a name. E is another one that comes up really, really frequently, so we gave it a name. And it is 2.7183, blah, blah, blah. It goes on forever. Now, if you really want to know where it comes from, it's the limit as n goes to infinity of 1 plus 1 over n to the n power. So if you do 1 plus 1 over a quadrillion to the quadrillion power, you get really close to e. If you go even further than that, if your n gets even bigger, you get even closer to e. That's what the whole limit thing means. It's not important that you understand that. But what is important to know is that this number comes up in a lot of natural, real-world situations, in a lot of places in nature where things are growing at some sort of exponential growth. So this happens in radioactive decay, interest formulas, in lots of places where we let an n value go to infinity. So this number comes up a lot, but it is just a number. So if I asked you for e to the 5th power, you could actually calculate that because e is just a number. Your calculator has an e button on it as well. But anyhow, the big idea here is that natural log means the same thing as log base e. And so it undoes e to a power. It's the inverse of e to a power. But that's the definition. It's a natural logarithm. And again, it's ln. It is not in. So ln of x is just a shorthand way of saying log base e. So let's go ahead and do another one of these quick, easy examples. We're asked to calculate or to approximate the natural log of 8, rounded to 4 decimal places. And again, this is ln, not in. So if I want to do the natural log, that is the ln button, followed by 8. And when I hit enter, I get a value, 2.0794. And we can see the 5th decimal place was another 4, so we're not going to round up. We're going to keep it at 4, and it's as simple as that. So plugging numbers in, we can plug in common logarithms of base 10. We can plug in natural logarithms of base e. Just plug it in the calculator, get an answer, nice and easy. So if you remember in our last lesson, we talked about the inverse relationship between logarithms and exponentials. And in particular, we had said log base b of b to the x. We could basically say that the log undoes the exponential and leaves us with just the x. So in terms of these two logarithms that we're dealing with now, we can say, well, if I have common log, which is base 10, of 10 to the x, then the common log and the 10 to a power undo one another and leave us with just x. Similarly, if you had natural log ln of e to the x, then the log base e and the e to a power undo one another and leave us with just x. Now we could do similar with the other inverse relationship that's not as important. What I have written here is the most important part. But remember that we also had b raised to the log base b of x equals x. So similarly, we could say 10 raised to the common log of x would also be x, as e to the natural log of x would also just be x. Let's go ahead and see that in use now. Let's see if we can simplify a bunch of these logarithms here. So this first one, common log of 10, we want an exponent on there, so we assume this exponent of 1. Then the common log and the 10 to a power undo one another and leave us with just the 1. If I want to take common log of 1,000, I want to rewrite this as 10 to a power. And so remember that when it comes to 1s followed by a bunch of zeros, it's 10 raised to the power of however many zeros you got. So 1,000 would be 10 to the 3rd power. Then the common log and the 10 to a power undo one another and leave us with just 3. Now, like we saw in the last lesson, when you have fractions, in particular 1 over, you want to think about this as a negative exponent. So 1/10 is 10 to the negative 1st, at which point the common log and the 10 undo one another, leaving us with just -1. We had also talked previously about the fact that radicals should always be written as powers. That way we can handle them like powers. The square root should be the 1/2 power. Now the common log and the 10 to a power undo one another, leaving just 1/2. When it comes to natural log, remember that natural log undoes e to a power. So this natural log undoes e to the power of 3, leaving just the 3. And if we had a radical, we would rewrite it as a power. So instead of the 5th root, we'd have the 1/5 power, at which point the natural log and the e to a power undo one another, leaving us with just the 1/5. And so hopefully you have some experience with the generic logarithms of any old base that we've done previously. And so now we're just dealing with 2 special bases. Base 10 for common log when you don't write a base. And if it's ln for natural log, then we assume the base is e. So let's take a look at solving some equations that involve the common log or the natural log. So remember, when solving logarithmic equations, the big idea is to take the base raised to the power of the opposite side equals the argument. So in this first example, my base is 10. It's not written, but remember, common log means base 10. Raised to the power of the opposite side equals the argument. Now, if you were being asked to give an exact value, at this point, you're done. Now, if you wanted an approximate value, we could go ahead and type this in the calculator and do 10 raised to the power of 1.2. And we could say it's 15.85. But again, remember, this is exact when we don't put it in the calculator, and it's approximate if we do put it in the calculator, because we've got to round somewhere. Now, if you have a natural logarithm equation, you again want to take the base raised to the power of the opposite side equals the argument. But in this case, the base is e. We raise it to the power of the opposite side, and that equals the argument. Now, in order to finish solving this equation, we need to divide both sides by 3 in order to get the x by itself. That would get us e to the 5th divided by 3. This would be our exact answer. It's okay to leave the e in the answer. Now, if we did want to get an approximate solution to this, we could put this into our calculator. So e in most calculators is second followed by the natural log. Because it's the inverse, it comes there a lot. So we just take e to the 5th and divide by 3, and we get about 49.47. And this, again, is what we would call the approximate solution if we're being asked to round to a certain number of decimal places. The next thing I want to look at is a very specific type of word problem that involves a common log. And these problems, quite frankly, are going to be some of the easiest problems that you're ever going to deal with. They're to talk about the Richter scale. You've probably heard of the Richter scale before and how it measures the intensity of an earthquake. So it does involve common logarithms when calculating the value on the Richter scale, the intensity or magnitude of the earthquake. Now, the formula to get that value that you hear on the news is the common log of a divided by t plus b, where a is the amplitude of the seismic waves of the earthquake itself, and they're measured in micrometers. But this is how much the ground moved up on a wave of the earthquake. Now, the capital T is the number of seconds between successive waves, so between when the ground moved up and it moved up again. B ends up being an adjustment factor that's brought into play based on a couple of factors. The most important factor is how much earth is between the epicenter of the earthquake and your measuring station, wherever it is that you're measuring these seismic waves, because quite obviously the seismic waves are going to dissipate a bit as they go further out. If you're 100 miles from the earthquake, you're not going to feel it nearly as strongly as if you were right there on top of it. So this B value helps account for that difference there. Now, the problems that we're going to deal with, let me get this all on the same screen here. You're going to be asked to find the earthquake's magnitude on the Richter scale if the recording station measures an amplitude of 300, 2.5 seconds between waves, and B is 4.2. So literally all this question is going to be is plugging numbers into your calculator. Because you're going to say it's log of A was 300, T was 2.5, and the B value was 4.2. So you're just going to literally plug those numbers into your calculator. I'm going to move that over a little bit so we can see the problem still. And so you're just going to type in log of 300 divide by 2.5, end my parentheses for the log, but then plus 4.2. So this was a 6.3 on the Richter scale. Now this is, quite frankly, a very easy problem, but I want to talk about this so that we can sort of start to understand the Richter scale, and we can start to understand how intense an earthquake is and the difference between, say, a 6.3 and a 7.3. Because some people might say, well, the difference isn't much, it's, a sixth higher is all it is. But the difference between a 6.3 and a 7.3 is actually 10 times stronger. Because think about how you graph logarithmic functions. In order to take one step up in the y direction, you need to multiply the x value by the base, which is 10. So that means in order for our Richter scale to go up by 1 unit, the argument, or what I plug in, needs to be 10 times higher. So what's the difference between a 6 and an 8? An 8 is 100 times stronger because it's 10 squared. The difference between a 6 and a 9 is 1,000 times stronger. So hopefully this starts to make some sense when you start to hear about some of the world, famous 9-point whatevers that do such incredible damage and cause typhoons. You can start to understand, oh, even though a 9 compared to, say, a 5, where a 5 is bad, if I compare a 5 to a 9, that's 10,000 times stronger. It sounds like it's maybe not quite double the strength, but obviously it's not. The amplitude is much, much different. So that's why I want you to see how to understand a common logarithm. And so when you start to see things that are based on common logarithms like the Richter scale, you can start to get an appreciation for them. So I want to remind you that we've talked about compound interest in the past, where we had a equals p times 1 plus r over n all to the nt power. But I want to remind you also, though, that I defined e as being the limit as n goes to infinity of 1 plus 1 over n to the n power. So notice we've got 1 plus something over n to the n power. Now I'm not going to go through a full proof of this, but I want to point out that if we let our number of computations come close to infinity, it looks like an e is going to pop out. So what does this mean to let the number of computations go to infinity? Well, daily interest, your n would be 365. If you had hourly interest, you would take that 365 and multiply by 24. Let's get out our calculator and do that. So if you had hourly interest, you'd multiply that by 24. Say, all right, well, what if instead of hourly interest, I had minutely interest? We could multiply that by 60. Well, what if instead of minutely interest, I had secondly interest? So times 60. So that's a huge number there. And then say, what if instead of every second, I did every millisecond? So I multiply this by another big number, like 1,000,000. So all of a sudden, our n value is getting bigger and bigger and bigger to say, well, let's just continuously compound interest. Every millisecond, every nanosecond of every day, we're continually compounding interest. Well, that would turn into an n being infinity situation. And when that happens, your compound interest formula turns into a equals p times e all to the rt power. So let's look at an example that uses continuously compounded interest. It has to find the amount owed at the end of 5 years if $1,600 is loaned at a rate of 9% compounded continuously. So the formula in question here is A equals P times e to the RT. The A value is what we don't know. We know the P value is 1,600, the R value is 0.09, and the T value is 5. So if I plug those values in, this is another super easy word problem because it's just straight up a calculation. There's nothing to solve, no algebra to do, just plug and chug. So 1,600 e raised to the 0.09 times 5. 2509 and 30 cents. So sure, we can figure that out, we write that answer. But what might be a little bit scary is to think that this is perfectly legal to have continuously compounded interest, to say, I'm going to borrow some money from the bank and they're just going to continuously charge me interest. Not even just say at the end of the day I get interest. It's every second of every day I'm getting interest. That sounds very stressful. What I want to do now, though, is I want to do a little comparison and just say, what if it was daily interest instead? Let's look at how different daily interest would be, because daily doesn't sound nearly as scary. So the formula would be A equals P times 1 plus R over N to the NT power, where everything stays the same as the other version, only we have an N value of 365 instead of N equal infinity. So let's plug those numbers in. We'd have 1,600, 1 plus 0.09 over 365, all to the 365 times 5 power. And let's get our calculator out and do some work with that. I'm going to move the calculator over here. So 1,600 parentheses 1 plus 0.09 over 365 all to the power of 365 times 5. Now, if your calculator doesn't have the nice little exponent like mine does, then you're going to want parentheses around your 365 times 5 to say all of this happens in the exponent together. Now, as I hit enter here, it makes it so that continuously compounded interest doesn't sound nearly as scary. The amount that we owed if it was daily interest was 14 cents less than continuously compounded interest. So by continuously compounding the interest, instead of just doing it at the end of the day, the bank made 14 cents off of us over the course of 5 years. So less than 3 pennies per year. But guess what? Might not sound like a lot to you, but I bet the bank is happy with that, because they're 3 cents off of each person. If they have 1 million people, that adds up. So it's something to think about when you're looking at the fine print on the loans that you're signing up for. So I'm bringing back a little blast from the past for a second. So this was a few lessons ago, and we were looking at trying to solve exponential equations. In this exponential equations that we were trying to solve, we were making the bases the same. So if you look at these examples from left to right, we said let's make the bases both 2 in the first example. Once the bases were both 2, we matched up their exponents, solved the equation. Second example, we made both bases 3, said awesome, now their bases are the same, their exponents must be the same, solve for x, blammo, awesome. A little trickier in the third example here, we said let's make both bases 2, and we did that by making it 2 to the 0, but then bases were the same, so exponents were the same, solve for x, piece of cake. But when we got over here to 4 equals 3 to the x, we said, I don't know how to do that. I don't know how to make both bases a 3. So I just couldn't do it. I couldn't solve that particular exponential equation. But now we're at the next level of the course. Now we're going to look at saying, maybe I can solve that still. So we're going to look at 3 to the x equals 5, and we're going to try to use logarithms to solve it. And I want to talk about 3 different approaches to this same problem and how we can get an answer in all 3 ways. So the first way that I would probably try to solve this would be to directly undo the exponential. So we actually kind of already talked about this a little bit, how to say, let's get rid of the exponential by applying the appropriate base of logarithm. So let's take log base 3 of both sides, so that log base 3 and 3 to a power undo each other, and x is log base 3 of 5. And that basically solves the problem. Great. X equals log base 3 of 5. Now put that in your calculator. I don't know how to do that. That's a problem. Now, some calculators will allow you to put in bases other than 10 and e, but a lot of calculators only have common log and natural log to them. So let's talk about another approach that we could have taken to this same problem. 3 to the x equals 5. So instead of taking log base 3 of both sides, which was a very ideal thing to do, we could say, let's use something that's in our calculator, common log. Now, common log doesn't undo 3 to the x, but I can use my properties of logs. Because I've got a property of logs that says if there's a log in front of here, we can bring that exponent down in front as a coefficient. Now, this is x times log 3. Log 3 is just a number. So I have a number times x. If I want to solve that, I would divide both sides by that number. And that gets me a solution to the equation. X equals log of 5 over log of 3. Now, if we look at what we did in this second example, we never used the fact that that log was base 10. We just used the fact that it was any old log. So I could have did the exact same thing with natural log as well. I could have had natural log, and I could have brought the x in front. And then I could have divided by the natural log of 3. And came to an answer as well. And all 3 of these answers better be equivalent. And realistically, I could throw a 4th thing in here if I really wanted to. I could say, oops, let me use blue just to stay consistent over here. I could say log of any old base I want, log base b. And I could do the same thing, and what's going to end up happening is I'm going to have log base b of 5 over log base b of 3. So the reason I actually wanted to show you this was actually to come up with this thing called the change of base theorem that you definitely want to write down, highlight. It's a formula that you need in your notes. What we just showed is that we showed log base 3 of 5 was the same thing as the common log of 5 over the common log of 3. And that was also the same as the natural log of 5 over the natural log of 3. And really, we could do that with any old base we want. So if I want to write this in terms of some general formula, then let's ignore this by calling this b over here, because I'm going to reuse b for something different. I'm going to say, suppose I have log base b of x. Then I can rewrite that as the common log of x over the common log of b. Or I could write it as the natural log of x over the natural log of b. And really, I could choose any old base I want. Oops. So I could do log base c. I could pick any old number I want, as long as the x is on the top and the base is on the bottom. Let me repeat that. As long as the base is on the bottom. That's something that we're going to talk about over and over and over again, is the base being on the bottom. It's a good way to remember what order the change of base formula goes in. That we want the base on the bottom, the base in the basement. That's one of the biggest errors I see people make, is flip-flopping the fraction. And so you want to avoid that. Now there's lots of purposes for the change of base formula as you move forward in math. What we're going to use it for in this class, though, is for calculating, or evaluating, I should say, evaluating logarithms that we normally couldn't put into our calculator. So that, for instance, if I wanted to evaluate log base 3 of 2, then in the calculator I could do log of 2 divided by log of 3. Again, the base goes in the bottom. And similarly for the second one, I could do log 2/3 divided by log 6. And on any of these, if I chose to do natural log instead, I could. I could do natural log of 8 divided by natural log of 6, as long as the base is in the bottom. The base is in the basement. So now for each of these, I could go ahead and use my calculator. So for that first one, I could do log of 2 divided by log of 3. And it's 0.6309. That's the first one. To do the second one, we've got ourselves log of 2/3 divide by log of 6. We get negative 2263. And then lastly, go and move my calculator over here so we can see it. Lastly, I chose to switch to natural log. Again, there's no reason for me to switch to natural log. I just want to show you that you can get a correct answer with natural log or common log, whatever floats your boat. We got 1.1606. Now, I do want to point out a couple things to remind you how you can easily tell roughly what your answer should be. So first of all, remember for a logarithm, all of these bases we were looking at were larger than 1. So a logarithm graph, remember, looks sort of like this, where we know the ordered pair 1, 0 is right there. Now, keep in mind that log base 3 of 3 would be 1. So if I have log base 3 of 2, it's a little less than 1. Whereas to get 0, I know that log base 3 of 1 would be 0. 2 is somewhere between 1 and 3, which means my answer should be somewhere between 0 and 1. Now, as far as this 2/3 guy, log base 6 of 1 would be 0, whereas log base 6 of 1/6 would be negative 1. And I know that 2/3 is somewhere between 1/6 and 1. So this negative number that's between 0 and negative 1 makes sense. For this one, log base 6 of 6 would be 1. And log base 6 of 36, which is 6 squared, would be 2. 8 is somewhere in between 6 and 36, so my answer should be somewhere between 1 and 2. And it is. And this just gives us an idea to make sure that we're in the right ballpark, to make sure we didn't make a mistake. All right, so we actually looked at an example like this not that long ago, but I just want to reiterate how we can solve this where we can both get an exact value as well as be able to put it in the calculator. So while we could just take log base 2 of both sides in order to get rid of the exponential, we're actually not going to do that. What we're typically going to do instead is just say, let's just take any old log, one that we can put in the calculator, of both sides. By taking common log of both sides, we can apply the property of logs, the power property that says, put that x in front as a coefficient. And now that I have log of 2 times x, I can undo that multiplication with division. And this is typically how we prefer to actually solve these equations, because oftentimes we do want to get an approximate solution, so we do want to put it in the calculator. Now, this is an appropriate exact solution or exact answer, and then if we did want to put this in the calculator, that's what's going to get an approximate solution. And so to do that, we would just type in log 3 divide by log 2. We're going to get 1.5850. And there's the approximate solution to a problem like this. All right, so now we're going to step it up a little bit in difficulty. So now we have an expression in the exponent. Now our game plan stays the same though. I'm going to go ahead and rewrite this with a little space over here. We're still going to take just a common log of both sides. And again, the purpose of this common log is just so that we have a logarithm in place to be able to use our properties of logarithms. So now in doing so, I can take the whole exponent, the whole 2x minus 6, and bring it down in front as a coefficient. Now we've dealt with problems similar to this before, but I want to go ahead and go through two different approaches that we could take to this problem that are both going to get us the same answer, but the answers might look a little bit different. Now one approach that we could take at this point is to divide both sides by that log 5. That would give us 2x minus 6 equals log 12 over log 5. At which point we could add the 6 to the other side. So we have 2x equals log 12 over log 5 plus 6. So we added the 6 to the other side. And now to divide by 2, what I would do if I were you is think about this as multiplying both sides by 1/2. It's a little bit easier to think about it this way when we're dealing with fractions and distribution and everything that has to happen on the right. So this would get us the x by itself. Now when I distribute the 1/2 to the log fraction here, that's just going to put a 2 in the bottom. 1/2 times 6 gets us 3. Now at this point, if I were you, I would have bought the $10 calculator instead of our nice graphing calculator. And so let me show you how easy it is to put this into the nice, simple $10 scientific calculator. So in our nice, simple $10 calculator, we just hit the fraction button. After hitting the fraction button, we can type the log 12 on the top, arrow down to the bottom for 2 log 5, arrow out of the fraction for the plus 3. And so we can get a nice answer of our 3.7720. Now, if you don't have that calculator, let me talk about what you need to do, and this is really important because this is where I see a lot of errors happening at. And it's one of the big reasons I suggested that cheap calculator in the first place. So, if we do log 12, divide by, here's the important part. We need parentheses for our 2 log 5. Those parentheses say all of this is in the bottom together. Let me actually change this over to classic so that you can see the whole thing at the same time together. So there's where all of my parentheses and everything need to be. So you can see all those parentheses to get that proper value of 3.7720. Now I talked about 2 approaches that we could take. So let me go ahead and rewrite this step over here just to point out another slightly different approach that will lead us to the exact same answer. We could have distributed the log 5 to get 2x log 5 minus 6 log 5. Some people like this better. I think it looks a little bit uglier, but you don't have to deal with the weird division thing of multiplying by 1/2 that we did. Now to solve for x, remember that's our goal, is to solve for x. We've got this value that I've just underlined that has no x's in it. So that's the first thing that we would add to the other side. That would get us log 12 plus 6 log 5. And then to get the x by itself, we divide by everything that isn't the x, which would be 2 log 5. And so this gets us an answer of log 12 plus 6 log 5 all over 2 log 5. Now this answer actually is equivalent to the other answer that we had written over there. The big difference is we basically found a common denominator and made it a single fraction. And then we could put this in the calculator as well. We would need to make sure that we have parentheses around the entire top and around the entire bottom. So now let's take a look at a word problem. This one has to do with an exponential equation still. This says the number of victims of a flu epidemic is increasing at a rate of 7.5% per week. And you'll notice that I bolded per week here. If 20,000 persons are currently infected, find in how many days we can expect 45,000 to have the flu. Okay, so a couple important things here is, first of all, the thing that I bolded here, you'll notice that our units aren't matching up, so we've got to be careful with units and how we calculate this. Now when you see y sub 0 always means your initial amount, how many you started with. So in this case, our y sub 0 is our initial amount of 20,000. Our future value of y is how much we ended up with, which was 45,000. Our t is unknown, but t is going to be in weeks when we calculate it. So to answer the question, we're going to have to figure out how many days and have to multiply by 7. So we just got to be careful there. So our equation tells us we have 45,000 equals 20,000 e to the 0.075t. So in order to solve this exponential equation, and this is an exponential equation because we do have some number, e, raised to a variable power. In order to solve this exponential equation, we want to get the exponential part by itself. So we need to get rid of the 20,000. Now be careful, one of the tempting things to do here is to subtract 20,000 from both sides. Subtraction undoes addition. This was multiplication. So we need to use division to undo the multiplication. And so 45,000 divided by 20,000, the thousands divide out, and then really 5 goes into each of those. So it really just goes down to 9/4 without too much math at all. Now to undo e to a power, we have an obvious choice of natural log, because natural log, remember, is log base e, so it'll actually directly undo this. So the natural log undoes e to a power. And that gives us the natural log of 9/4 equals 0.075t. So to get the t by itself, we just need to divide both sides by 0.075. So now I'm going to get out my calculator, and I'm going to have the natural log of 9/4 on the top and 0.075 on the bottom. And I get this number 10.81 something or other. But remember that this is measured in weeks. So I need to multiply this by 7 to figure out how many days, because that's what I was asked about. So just to be a little bit picky here, we're looking at about 76 days is the answer we're looking for. Let's look at one more word problem that leads us to an exponential equation that we want to solve. And this one says that we deposit $2,800 in an account that earns 4.8% interest compounded quarterly. And we want to know how long it'll take for the investment to earn $2,331 of interest. This is a little bit of a tricky problem, actually. So let's talk about it. First of all, I like to write down the controlling formula. So we got the compound interest formula. When using a formula such as this, I'll then jot down all the variables involved in the formula and try to fill in as much as I can. So the $2,800 was the initial amount we put in. That's a p-value, principal. Our interest rate of 4.8% would be 0.048. It's compounded quarterly, so remember n is the number of computations per year, and so quarterly would be an n of 4. Now we're asked how long, so time is going to be the variable. But let's talk about a. The tempting thing for people to put for a is 2331. That would be incorrect. Now, first of all, that means you lost money, so hopefully it's clear that that can't be it. Remember, a is your final amount. So if we started with 2,800 and we had interest of 2331, then it looks like our final amount should be 5,131. Make sure to use a little bit of common sense on these problems. Think about really what's going on in these problems and say, A is how much I end with. If I started with $2,800 and I end with $2,300, I lost money. That's not good for an interest-bearing account. So think about these and make sure they make sense. So we're going to plug 5131 in for A, 2,800 for P, 0.048 for the R, 4 for the N, 4 for the N, and T. This is another example of an exponential equation. We have a number raised to a variable power. That means we want to get that by itself. So what we don't like is the 2,800. We need to get rid of the 2,800. Just like the last problem, that means we're going to divide by it, because it was 2,800 times parentheses. Now this is going to end up being a calculator problem in the end. So I'm not going to bother putting this into the calculator, this 5131 divided by 2,800. I'm just going to leave it there. And really, same thing with this other piece. Even though this does simplify to be a nice, happy number, I'm going to leave it there just to point out what happens when it doesn't work out nice. So now I have an exponential equation, or in other words, I have an exponent in my variable. To get the exponent out of the variable, take a log of both sides. By taking the log of both sides, we can bring the exponent down in front as a coefficient. Have 4t log 1 plus 0.048 over 4, and that's equal to log 5131 over 2800. Now, something I want to point out about that 4t over there is the order of 4t doesn't matter. So even though it looks kind of weird, I'm going to rewrite it as t times 4. And for that matter, I can put the t over here. So that what I have here is just my coefficient of t. It's all it is. So I could divide both sides by 4 log 1 plus 0.048 over 4, and I can get an answer. Now again, if we're using the cheap calculator, this is really easy to type in the calculator. We're typing in the left-hand side because everything else went away and left us with just t. So I'm going to hit the fraction button, log, fraction button, 5131 over 2800. Close that parenthesis and arrow down to the bottom. 4 log 1 plus fraction button 0.048, arrow down to the bottom for my 4, and we can literally type this exactly as it appears on our paper. Hit enter and we get an answer of 12.69 years. And this should make some sense that our money almost doubled, so to take about 13 years to double should make sense. Now, if we are using the non-fancy calculator, we got to be just a little bit careful with parentheses is all. So we could still type the log 5131 divide by 2800, then divide by, now we need parentheses to say all of this is in the bottom together for our 4 log 1 plus 0.048 over 4, and the parenthesis for the log, and the parenthesis for the denominator, and we do in fact get the same answer. So now let's switch gears to talk about solving logarithmic equations. Now we've really already been solving logarithmic equations, but I want to talk about it in a little bit broader sense than we've done already. Now the most basic type is what we've already solved, where we have a single log on one side and a number on the other. And when we see that, we say, okay, I can solve that. I'm going to take the base raised to the power of the opposite side equals the argument. So in this case, that would look like 3 raised to the 2 equals x. So x is 9. Nice and simple. Now, every logarithmic equation we ever deal with is basically going to boil down to this. Get it so that it's single log on one side, number on the other, and undo the log. Undo the log by taking the base raised to the power of the opposite side equals the argument. So what's going to happen, though, is that these are going to get a little trickier. So in this case here, we don't have a single log on one side, so we make it that way. And that's what we did earlier on this lesson, is we learned how to do that. We learned how to use the properties of logs to do that. Or actually, we did it last lesson, excuse me. So we use the properties of logs to say, hey, if I'm adding 2 logs together, then I can multiply their arguments. Now that I have a single log on one side, number on the other, then I can take the base, raised to the power of the opposite side, equals the argument. And now our last step says, solve the resulting equation. So to solve this resulting equation, to get the x by itself, I just divide both sides by 5. And that's going to get me x equals 3/5. At its core, that's all we're going to be doing to solve logarithmic equations. As we go through the next couple examples, though, we're going to see that a few tricky things come up, but for the most part, this is how it's going to boil down. It's going to boil down to make a single log on one side, number on the other, take the base, raise to the power of the opposite side equals the argument, and then just solve whatever's left. So let's look at these two examples. Now the first one we're looking at already has single log by itself on one side, number on the other. So this means we can take the base, raise to the power of the opposite side, equals the argument. Now to solve the resulting equation, we look at this and say, hey, this is quadratic, so let's move everything to one side so that the other side is 0. Then to solve a quadratic equation, we try to factor. If it's not factorable, we use quadratic formula. Now this one actually is factorable, so we're going to factor it as x minus 3 and x plus 2, meaning either x minus 3 could equal 0 or x plus 2 could equal 0, meaning x could be 3 or negative 2. Now both of these answers are in fact going to work, but I do want to tell you that when it comes to logarithmic equations, this is going to be a case where we should check our answer to make sure we didn't get an extraneous solution, an extra one that needs to be thrown out. And what we're looking for is we need to make sure that whatever answers we get make our arguments positive. Because remember that we can't take the log of a negative and we can't take the log of 0. We can only take the log of a positive number. Now this x equals negative 2 was fine because the argument was positive. If we looked at plugging negative 2 in, we would have negative 2 squared minus negative 2 on the left, so that would be 4 plus 2. And log base 6 of 6 really does equal 1, which is what I was trying to equal. So that negative 2 really did work. And quite frankly, the only thing that's going to run us into problems is this second example, when we have to use a property of logs. So when we use a property of logs to make a single log, that's when we got to be careful. So on this one, we're going to use a property of logs to write this as a single log, making this log base 3 of x times x plus 6 equals 3. Then we can take the base, raise to the power of the opposite side, equals the argument. Now since this is quadratic, we can move everything to one side. So we're going to subtract the 27 to the other side. And then we're going to factor. And this factors as x plus 9, x minus 3, meaning x plus 9 could be 0 or x minus 3 could be 0. Meaning x could be negative 9 or x could be 3. But remember, what we want to look for, what we're double checking, is that in the original problem, that none of our arguments were, to be technical, non-positive. So we want to make sure that the arguments are in fact positive. So if I were to plug negative 9 into the original problem, that argument would be negative. So as we saw in the first example, a negative answer isn't a bad problem. It isn't an extraneous solution. The problem is when an argument becomes negative. Now when I plug x equals 3 into the first argument, that's positive. When I plug it into the second argument to get 3 plus 6, that's positive as well. So x equals 3 is perfectly fine. Now, it is possible to throw a positive answer out as well. So I just want to point out that if your original problem had something like log of 2 minus x, and you got x equals 3, that would get thrown out because your argument was negative 1. 2 minus 3 is negative 1. That would be bad. So what we're looking for is we're making sure that the arguments in the original problem are always positive. That's what we got to be careful of. That's what we got to look out for. Let's go ahead and look at the last example of the year. So for this example, we have a logarithmic equation. Our goal is to make a single log on one side, number on the other. This time we have subtraction between the logs. So that means to make it a single log, I turn this into a division problem. The first argument divided by the second argument. Now I take the base, raised to the power of the opposite side, equals the argument. This is a rational equation, and so we go through our normal routine of saying fractions suck, get rid of the fractions. Let's multiply both sides of the equation by x. On the right-hand side, those x's will divide out, and that's going to leave us 4x equals x plus 4. Let's get all the x's to one side, so let's subtract an x to the left. Let's divide by 3 and get x equals 4/3. 4/3 would be perfectly fine in the first argument. The first argument of 4/3 plus 4 is positive. The second argument would just be 4/3, so that's positive. So this value is perfectly fine. Now, in terms of the whole course, keep in mind there's been 3 times you have to check your answers. The first time was rational equations, which really happened in this problem as well, since we did have an x in the bottom, and we needed to make sure that the denominator didn't equal 0. The second time is anytime you square both sides. Now this came up often in square root equations when you had a square root on one side and a number or an expression on the other side. In this case, we had to check the answer fully. We had to really make sure that it worked in the original problem. And the third time we've had to check our answer is log equations. And with log equations, we had to make sure that the argument was positive. So make sure to know those 3 cases. We are here at the end of the course, which means the final exam is right around the corner. And so you got to think about this, because come final exam time, you want to make sure you know when you have to check your answer versus when it's just a good idea. Because obviously we want to check our answers to make sure that we're not making mistakes. But there's the times that you have to check your answers, like those 3 times. All right, hopefully you've enjoyed this course, and good luck wrapping it up with the final.